Okay, so in this video we're going to talk about linear and nonlinear systems of inequalities. First we'll start with linear inequalities in two variables. So let's define what a linear inequality is. A linear inequality in two variables is an inequality of the form ax plus by less than c, or any other inequality replacing that symbol there. So it's basically like the equation of a line in standard form, but the equal sign is replaced either with a less than or equal, greater than, or a greater than or equal symbol. And also we have the corresponding nonlinear inequality in two variables, which is an inequality where the expression contains variables with exponents different from 1 and or variables multiplied together. So for example, we have y greater than x squared minus 4, or for instance, the ellipse here, x squared plus 3y squared less than or equal to 9. And we'll see some examples. Okay, so what does it mean to solve a linear inequality? Well, let's discuss what a solution is. So a solution to such inequalities is an ordered pair of real numbers, x and y, that satisfy the inequality. So the graph of an inequality in two variables is the set of all ordered pairs x, y that satisfy the inequality and can be visually shown as a region in the xy plane. Okay, there's going to be too many values that satisfy the inequality. And so we have to represent it using a graph if you want. Okay, so consider the linear inequality 2x plus y less than 3. While an ordered pair such as -3, 5 is a solution to the inequality, since when you substitute the x and y into the left-hand side of the inequality, we would get 2 times -3 plus 5, which is -6 plus 5. That gives us -1, and -1 is less than 3. However, a point like, or an ordered pair like 4, 3 is not a solution, since when you plug this point into the equation on the left, or the expression on the left, we have 2 times 4 plus 3, which is 8 plus 3, which gives us 11, and 11 is not less than 3. Okay, so that's false, and therefore it's not a solution. So there are many solutions to this inequality, and is visualized as a region. Consider the region below the graph of 2x plus y equal to 3, which is drawn as a dashed line or a dotted line. So you can see here, this is the line here, 2x, this line here is the line 2x plus y equal to 3. Okay, so those are the points that fall on the line, and the reason why we draw it as a dashed line is because no point on this line satisfies the inequality 2x plus y less than 3, because it equals 3 and 3 is not less than 3. However, the points here where we had -3, 5 was one point. That point there falls on the side that's shaded because it's a solution. And so any other point on this side of the line, or in this region, oftentimes referred to as a half plane, will satisfy the inequality 2x plus y less than 3. And so that whole region there, shaded there, is the solution set to the inequality 2x plus y less than 3. Anything out here, such as we observed 4, 3, did not satisfy the inequality, and therefore no other point out here will as well. Okay, so that's a linear inequality. However, of course, we just defined also what's a nonlinear inequality. And so here's another example. So another example, consider the inequality x squared plus y squared greater than or equal to 16. Well, the solution set of the inequality is all ordered pairs that make up the circle x squared plus y squared equal to 16, and all ordered pairs that are exterior to the circle. The graph of the inequality is represented by the shaded region, and the solid line represents the circle. Okay, so any point on the circle itself, so any point going on the actual circle, and I can't for some reason draw a circle correctly here. Okay, this is the circle x squared plus y squared equal to 16. And so any point on there, when you plug into the equation x, and for y, you get x squared plus y squared, which gives you equal to 16. And therefore 16 is greater than or equal to 16. And that's a true statement. So any point on the circle is a solution. Likewise, any ordered pair that's in the shaded region will also satisfy that. Okay, so for instance, if we take this point here, which has coordinate 0, 6, you plug 0 for x and 6 for y. So you get 0 squared plus 6 squared, which is 36. 36 is greater than 16, and therefore satisfies the inequality. And so all the solutions that satisfy the inequality are on the shaded region, and including the boundary or of the region, or the basically the equation x squared plus y squared equals 16. Okay, so visually that's how it looks, and so algebraically it's hard to express all those answers, and I can't list them all because there's just uncountably many of them. And so the strategy to figure out the solution set is basically to visualize the solution set and graph the inequality. So here's the procedure we could use. All right, so the procedure is graphing an inequality in two variables. So so first step is replace the inequality symbol with an equal sign and graph the corresponding equation. Draw a solid line if the original inequality contains a less than or equal or greater than equal symbol. Draw a dashed line if the original inequality contains a less than symbol or greater than symbol. Step 2 is choose a test point from each of the regions the graph of the equation creates. Do not choose a point on the graph of the equation. Substitute the coordinates of these test points into an inequality. If a true statement results, shade the region containing this point. If a false statement results, do not shade the region containing this point. And so let's illustrate how to do that. Okay, so our first example here is to graph the line 2x plus 3y greater than or equal to 16. I called it a line, but it's a region. So 2x plus minus 3y greater than or equal to 16, this linear inequality. And then we're going to get step 1 says to basically take that same inequality, but replace the greater than or equal symbol with an equal sign, and then graph the equation that results. So in this case, this is nothing more than a line in standard form. And when it's like that, I prefer to use the x-intercept method, x-y-intercept method, which is finding the x and y intercepts. So to find the x-intercept, we set y equal to 0, which basically eliminates the y term, or excuse me, the y term. And now solve for x. So then if you do that, we get 2x equal to 6. And so divide both sides by 2, you get the point 3, 0. Okay, so then the y-intercept is basically setting x equal to 0 and then solving for y. So this time the x term goes away and we have negative 3y equal to 6. So divide both sides by negative 3 to get y equals negative 2. Okay, and so that's the first, that's figuring out what the details is to graph the line. So we're going to plot those points. So we have 3, 0, and 0, negative 2. And we're going to, since it's a greater than or equal symbol, this will be a solid line because when you plug in any point on the line, 6 for any point on the line will satisfy the equation 2x minus 3y equals 6. So this left-hand side would be 6 in the linear inequality. And so 6 is greater than 6, which is a true statement. So it satisfies the inequality. All right, so then we're going to graph these lines here. Okay, so it looks something like that there. And it's a solid line. And keep in mind this goes indefinitely in both directions there. And then we're going to take a test point. I'm going to take the test point to say 0, 2. Sometimes it's convenient to take some nice points on the axis since one coordinate 0. So I took 0, 2. And then I also chose the point, say 2, negative 4 off the line. And then I'm going to test these points in the inequality. Okay, so I'll just test these points. And can't seem to write here. Let's write down test points. Okay, so first point we'll test is 0, 2. Okay, and so we'll plug this into the inequality. And so we have 2 times 0 minus 3 times 0. And then we're checking to see if this is greater than or equal to 6. So question mark, is that true? And so 2 times 0 is 0. So we have minus 3 times 0, which is 0. So 0 minus 0 gives us 0. And is 0 greater than, I'm sorry, for some reason I plugged 2 in for 0 for, plug 0 in for the y coordinate, but it's 2. Okay, so it should be 2 there. So 0 minus 6. And so we get 0 minus 6, which is minus 6. And is minus 6 greater than or equal to 6? And that's definitely false. And so we do not shade the side that point falls on. And then now we test the other point here to negative 4. Okay, so plugging in the point 2, negative 4, we have 2 times 2 minus 3 times negative 4. And we're checking to see if this is greater than or equal to 6. So 2 times 2 gives us 4. Negative 3 times negative 4 gives us positive 12. So we get 16. Is 16 greater than or equal to 6? And that is true. Okay, and so what we're going to do is shade the side where the point's at. And so we would shade the corresponding side here, because any point on this side would satisfy the inequality. Okay, and so that's the solution set. And quickly here, I want to show you how to use, say, Desmos, or I'm sure other graphing calculators can do it similarly, but we'll look at Desmos here and show how you could graph the inequality as well. So Desmos is really nice in the sense that it will graph an inequality for you by just typing it in. And then, so it's greater than or equal to 6. And you can see you get the same region here. Okay, so let's go back to the notes for the next example. Okay, so we are asked to graph 9x squared plus 4y squared less than 36. Okay, so first step is always to replace that inequality. Oops. The inequality with an equal sign. Okay, so if you don't recognize this, this is just the equation of an ellipse. And so I'm going to go ahead and divide both sides of this here by 36. So this way we get the equivalent equation x squared over 4 plus y squared over 9 equal to 1. Okay, so this is an equation of ellipse where the center, it will be centered at 0, 0, and it would have vertices, which are just the extreme ends of the ellipse, which in this case are going to happen going vertically on the y-axis. And so it's going to have the form 0 plus or minus b in this case, or plus or minus a, depending on what form you're following. But it would be 0 plus or minus 3. I'm just going to write them as ordered pairs here, 2 ordered pairs, so 0, 3, and 0, negative 3. And then sometimes called co-vertices or vertices on the minor axis. In this case, it's going to happen going horizontally on the x-axis at 2, 0, and negative 2, 0. Okay, so those are important to draw our ellipse here. And one other thing to recognize is that when we draw this ellipse, we do have a less than symbol, which means it's going to be a dotted curve. Okay, so then plotting these points here, 0, 3, and negative 0, negative 3, and then 2, 0, and negative 2, 0 gives our extreme of our ellipse. And then I'm going to do my best to draw somewhat of a looking like ellipse here. And it should look something like that there. And there we go, there's our ellipse. Okay, once again, these are dotted because no point on the graph of the ellipse will give us something that is less than 36. In fact, you can check that by just plugging in your value. In fact, it gives you when you plug in your x and y, any point on this ellipse, you plug it into the original equation, to the equation we graphed, 9x squared plus 4y squared equals 36. When you plug it in any point on the ellipse, you get 36 on the left-hand side of the inequality, and 36 is not less than 36. So it doesn't satisfy it. So going with what we did last time, we're going to take a point, say, I'm going to take that point interior, say at the center, 0, 0, and then I'm going to take a point somewhere else that's in the exterior, say at 3, 4. Okay, so plugging in our test points now. We have test points. We'll plug in 3, 4. So 3, 4. Into our original inequality here, we have 9 times 3 squared plus 4 times 4 squared, and less than 36 here. And so that's the question, is this true? And so we get 9 times 9 plus 4 times 16. And so we got 81 plus 64, and 81 plus 64 gives us 145. And is this a true statement? Of course not. That is false. Therefore, we're going to be shading in the interior of this ellipse here. But let's make sure to check our point 0, 0. And so we got 9 times 0 squared plus 4 times 0 squared. Is this less than 36? And we could see we get basically 0 plus 0, which is 0. 0 is less than 36, so that's true there. Therefore, we shade the corresponding interior of this ellipse here. Okay, so that's our solution set. Once again, we should be able to do this in decimal, so let's go ahead and get rid of this particular region, and then actually type in our 9x squared plus 4y squared, and then less than 36. And you can see that the ellipse is dashed or dotted, and we're shading in the interior. Okay, let's go back to the notes. All right, so now that we've seen how to graph a linear inequality and a nonlinear inequality, we want to talk about a system of inequalities. Okay, so a system of inequalities in two variables is a system of two or more inequalities in two variables. Okay, so very similar to like our linear systems or linear nonlinear systems, we're looking basically all the solutions that satisfy both or all inequalities. So the solution set of a system of inequalities in two variables is a set of all ordered pairs that satisfy each inequality in the system. Okay, so let's look at this example here. So this would be considered a system of linear inequalities because each inequality is a linear inequality. All right, so our first graph here, I'll do it in blue here, x minus y, replace the less than symbol with equal to 1. And so let's go ahead and quickly here find the x-intercept. So set y equal to 0. So we have x equal to 1. The y-intercept, we'll set x equal to 0 and solve for y. So we get -1. So that's our ordered pair. And once again, we had a less than symbol, which means we're going to have a dashed line. Okay, so we have a point at 1, 0 and a point at 0, -1. And we're going to have a dotted line here, which goes like this, and then downwards like this. Okay, so that's our line that is dashed or dotted. Okay, and so then now let's go ahead and do the other one in red. So 2x plus 3y, and we're going to replace the greater than or equal symbol with an equal sign and 12. And just to remember, this is going to be a solid line because it's greater than or equal. All right, so once again, this is in standard form. So Once again, we're going to use the x-intercept and y-intercept method. And so set y equal to 0. That kills off the y term. So we have 2x equal to 12. So divide both sides by 2. We see we got 6 comma 0. All right, the y-intercept, we set x equal to 0 and solve for y. Okay, so the 2x goes away. So we have 3y equal to 12. So we get the ordered pair 0, 4. All right, so plotting these 2 points here. So 6, 0, and 0, 4. And then we plot our point, or excuse me, our line. Okay. All right, so it looks something like that. All right, so remember, points on the line could potentially solve the system or not. Okay, so let's figure out the regions to shade. And the way I do this is first I figure out which side of each inequality to shade. So for instance, I'm going to go ahead and take, say, a point, say it's above the test point, say -3, 0, and then maybe below, say at 0, -3, okay, and use those test points to test that inequality there. Okay, so then plugging it into the first inequality, x minus y less than 1, and so I plug it in, and I'll say get the point -3, 0, then we get -3 minus 0. Is this less than 1? And so of course that gives me -3 is less than 1, which is true. Okay, and then of course if I did the same point on the other bottom there, we could see that this should give us false, and I always do this just in case I make a mistake. Sometimes if you did it carefully, then you don't have to bother checking it, but I do it just in case I make a mistake. So 0 minus a -3, is this less than 1? Well, this becomes basically 0 plus 3, so 3 is 3 less than 1. That is false, so we won't shade that side. So what I like to do is then shade the corresponding side that goes that way. Okay, so that's my corresponding side going that way. And I'll adjust this in a moment, but right now that's what it looks like. That's the solution that satisfies the other inequality. Okay, so now, however, now we take some test points for the red, or excuse me, for the line 3x plus 3y equal to 12, or 2x plus 3y greater or equal to 12. So I'm going to take, say, a test point, and it could be the same test points you have if they fall on the opposite lines. But I'm going to choose the point, say, 0, 2, and then maybe a point above the line, say at 0, say 6. Once again, I'm choosing these ones just because they're nice and conveniently have a 0 coordinate for the x. Okay. All right, so let's test these points. Okay, so plugging this in, say 0, 2, we can see that the point here would be, we have 2 times 0 plus 3 times 2. Is this greater than or equal to 12? Well, that gives us 0, that gives us 6, so 0 plus 6 is 6. Is 6 greater than 12? And that is false. All right, so therefore, we're not going to shade that side of the red line. What about 0, 6? And of course, that should give us a true statement. So 2 times 0 plus 3 times 6. Is this greater than or equal to 12? So we get 0 plus 18. Is 18 greater or equal to 12? And that is definitely true. And so we would shade that side. And so the corresponding side to shade would be this stuff here, all the way across, going this way. Okay, so the solution set is essentially where they meet or where they overlap. Okay, and you can see that they're overlapping in the region here. So this region that I'm highlighting or in green, hopefully it comes out green, is the solution set. Okay, So all those points that are on the red solid line would work. All the points on the dotted blue line will not work, and they will not, the point at the very intersection where they meet there will not work. Okay, so it only works on the solid red part of the line, not on the dotted line, and everything up surrounded and going upward there, that's shaded in green. All right, let's see how decimals can handle this as well. Okay, so let's go ahead and get rid of this graph here. Okay, so we have x minus y less than 1. Okay, so that's what we graphed earlier. And then our second graph here was 2x plus 3y greater than or equal to 12. And let me just change the color so it corresponds to what I drew earlier. And we drew it in red. Okay, so it looks like this. Okay, so you can see it's the same region, but the region here where there's the overlap is the solution set. Okay, where they meet. So anything on the red, the solid line here, and anything on the dotted line, excluding where they overlap there, because 3, 2 would not work. It won't satisfy both inequalities, and anything on the dotted line would not work as well. Okay, so let's go back to the notes and try some more examples. All right, here's the next system. This time it's a little bit different because we have not just 2 inequalities, we have 3 inequalities. Technically, we kind of have like 4 equations here, but we'll discuss that in a moment. All right, so first inequality, I'm going to go ahead and do in black here, x minus y. And I'm going to replace the less than symbol with equals. Okay, and this is nothing more than a line. Okay, so we're going to have a dashed line in this case. And just to show a different way to graph this, so I'm going to go ahead and solve for y. If I do that, I get y equals x minus 2. Okay, so that means we have a slope of 1 and a y-intercept of 0, negative 2. So I'm going to go ahead and plot that point at 0, negative 2, and plot some additional points using the slope. So up 1 over 1, up 1 over 1, down 1 over 1, up 1 over 1, and so forth. All right, so let's go ahead and draw that in a dotted fashion or dashed fashion. It should look something like that. Okay, so there's our graph. All right, so that's one line. And then this equation here, this second equation, or inequality, excuse me, basically is 2 vertical lines when we replace the symbols with. So the first one is we're going to get x equal to negative 2. So this is basically a vertical line, and let me do it in a different color here. We'll do this in blue. X equals negative 2. And we'll also do the other one. X less than 4 corresponds to x equal to 4. Okay, so x equal to negative 2 is just a vertical line that passes through the x-intercept of, say, negative 2, 0. And x equal to 4 corresponds to the line, a vertical line passing through 4, 0. Okay, so we have 2 points at negative 2, 0 and 4, 0. Okay, and it's just a vertical line. Okay, now the first one, x equal to negative 2, we had a less than or equal symbol, and so therefore that is going to have to be a dashed line. And so I'm going to go ahead and do a solid line. I should say solid line. Solid line. Okay. And then x equal to 4 is going to have to be a dashed line. Okay. All right. Now the last inequality we have is y less than or equal to 3. So y less than or equal to 3 would be, I'm going to go ahead and do this in red here, is a horizontal line passing through the y-intercept of, say, 0, 3. And it is going to be a dashed line because of the less than symbol. Okay, so then at 0, 3, we're going to plot a point at 0, 3, and then a line that goes horizontally. All right, so there's our lines. Okay. All right, so this could be somewhat confusing. You could take a test point in all the regions and then test to see whether it's true or false. This would be time consuming though, but we'll approach it the way I approached the last one. Okay, so first off, I'm gonna choose a test point for the line, the line in black, x minus y equal to 2. So I'm gonna choose a point, say at the origin, 0, 0, and then to make this quick, another point on the y-axis, 0, negative 4. And let's go ahead and do some test the points. Okay. All right. So the first test point at 0, 0, we're going to get 0 minus 0. Is that less than 2? That's the question. And is 0 less than 2? And that is a true statement. The other test point I chose was 0, negative 4. So 0 minus a negative 4. We should get a false statement here. And that is 4 less than 2. And that is definitely false. So that means we're going to shade the side of the graph that is above. And let me do this again here, make this a little bit bigger so I don't have to. So it's all this stuff here, and of course beyond our coordinate system as well. So it's shading all that because that would satisfy x minus y less than 2. Okay, so there's that part. Okay, now let's take a test point, say, between the solid line and the dotted line. Let's go ahead and take, say, the point, say, here. Oops. Let's take the point here, say at 2, 4. And then we're going to plug it into our inequality, x negative 2 less or equal to x and 4. Well, the good news is that we only have to worry about the x value. So it's negative 2. And by the way, I probably should take another point, say off it. Let me take this point as well. 3, negative 2. All right, first let's test the point 2, 4. So is negative 2 less than or equal to 2? And is 2 less than 4? That is true. And let's go ahead and test the last point there, 3, negative 2. So this is the point for 2, 4, and this would be the point for 3, negative 2. So let's test it. So negative 2 less than or equal to 3 less than 4. And I realized that I picked a point in the interior of the two lines. So I'm going to have to back up there and don't take that point, because it's going to give us a true statement as well, which it should, because it's in the interior of the two lines. So if we took, say, a point to the left of the solid line, say at, say, this point here at negative 4, 2, we should get a false statement. And plugging it in, negative 2 less than negative 4 less than 4. Well, is negative 2 less than or equal to negative 4? That's no. Is negative 4 less than 4? Yes, but does not satisfy the double inequality. Therefore, this is false. All right, now take a test point, say, to the right of it, say here at, say, 6, 2. So is negative 2 less than or equal to 6? And 6 less than 4? No. It doesn't satisfy both inequalities, therefore it's false as well. Okay, so therefore we know the side we're going to shade has to be in the middle. Okay, so it's all this stuff here. All right, and then finally we have to test the red line, and I'm going to go ahead and just take, say, the point 0, 5 and the point 0, negative 5. And so testing 0, 5 into our inequality y less than 3. Well, is 5 less than 3? And that's a no, that's false. And so the other test point would be 0, negative 5. And so is negative 5 less than 3? That is true. And so we shade the side where 0, negative 5 is. Okay, which means we're shading below the red line, dotted line here. And we are finding where they overlap. Now they're overlapping in several places. However, where do they all overlap? And if you look closely, I'm going to try to do it in some green here. They overlap in this region here. So if I deleted the edges there, you would only see that middle triangular part shaded. And that would be the solution set there. All right, let's see how Desmos handles it. Okay, so let's get rid of this graph here, this graph here. So we have x minus y less than 2. And then we have -2 less than equal to x less than 4. Okay, and then y less than 3. Okay, so you can see that all the regions we shaded are pretty much the same, and they're going to all overlap at this region here. Okay, so interesting example. Let's go back to the notes to see another one. Okay, so in this example, we're actually graph the solution set of the system -x squared plus y greater than or equal to -4. So we'll do the first inequality, -x squared plus y, which we place the greater than or equal sign with an equal sign. So greater than or equal with an equal. So this happens to be a parabola. So we have y equals x squared minus 4, which basically gives us a parabola with vertex at 0, -4. And then just throw in some random some points to the right of it. Say x equal to 1, for instance. 1 squared minus 4 would give me 3. Then using symmetry, I have a point at -1, -3. Plugging in 2, so 2 squared would give me 4. 4 minus 4 is 0. So then using symmetry, I will have another point at -2, 0. Let's do a couple more points. So plug in 3. So 3 squared minus 4 gives me 5. And then using symmetry, we get another point at -3, 5. All right, so we have a parabola that looks something like this here. Okay. And so that's our parabola there. And then let's go ahead and graph the next inequality, which the equation of it, x minus y equal to 2, is basically the line in slope-intercept form as y equals x minus 2, which tells us we have a slope of 1 and a y-intercept of 0, -2. So plug in point at 0, -2. And then using the slope of up 1 over 1 or down 1 over 1, we get a line that looks something like this here. Okay. All right, so then now we take a test point. I'm going to go ahead and do the parabola first. So I'm going to take a point at 0, 0 and 0, -5. So 0, 0, 0, -5. Okay, so let's test the points. So let's test the point 0, 0. So we have -0 squared plus 0. Is this greater than or equal to -4? All right, so we get 0 on the left, but is that greater or equal to -4? That is definitely true. So we would shade within that parabola there. And just to make sure, 0, -5. So we have 0, -0 squared plus -5 greater than or equal to -4. So we get -5 on the left. Is that greater than or equal to -4? And that is false. Okay, so let's go ahead and shade the interior of that parabola there. Okay, so that's the shaded region there. All right, so then now let's do the same thing for the line. In fact, we're going to use the same test points because they happen to fall on both sides of the line. Okay, so let's test the test point 0, 0. So 0 minus 0, is that greater than or equal to 2? 0 greater than or equal to 2, that is false. Okay, and so what about 0, -5? So 0 minus a -5, is that greater or equal to 2? And that would give us 5. 5 greater or equal to 2, that is true. So we're going to shade below the line there. Okay. And so you can see that the region that's in common is basically where they meet in this little region there. All right. Next example. Graph the solution set of the system x squared plus y squared greater than 10, y greater than x. Okay, so let's go ahead and do the first one in blue. So x squared plus y squared greater than or equal to 10. All right. I put a greater than or equal symbol. I should have put an equal sign. All right, so this is nothing more than a circle centered at 0, 0, and with radius square root of 10. All right, to give me an idea of what square root of 10 is, I would take a calculator or something to give me an approximation of this, just to have an idea how far I'm going out. So this is about 3.162 da da da. Okay, so about 3.2. Okay, not much beyond 3. All right, so let's go ahead and plot the circle. So we know from 0, 0, we're going to go out 3 units horizontally, so 3.1 units horizontally, right about there, looks good. And then to the left, right about there, and vertically about there, and below, right about there. And so this will be a solid line because we have the less or equal. And so let's see if I could get a nice circle going there. All right, there we go. Nice circle there. All right, so now we'll do the other graph, which is y greater than x, but we're going to replace that with a greater than symbol with equals. So that's just the line that goes through the origin with slope of 1. Okay, so then it's going to be actually dotted or dashed. Okay, and going this way. Okay, so not the best line there, but it's okay. It will do. All right, let's take some test points. So let's do the circle first. I'm going to take the a point on the circle. The best point in the circle here is the center. So we'll take 0, 0. It's not on the equation of the circle, so I'm going to take 0, 0. And I'll take a point, say like 0, 5. All right, let's test 0, 0. Is 0 squared plus 0 squared greater or equal to 10, and the left side gives us 0. 0 is not greater than 10, so that's false. And so it looks like we're shading the exterior of that circle. But let's try 0, 5 just in case we messed up graphing it. So 0 squared plus 5 squared, is this greater or equal to 10? So we get 25 greater or equal to 10, and that is true. So we're definitely going to be shading outside of the circle. Okay, so shading our outside of the circle. Now we just got to figure out what part meets with the red graph, or excuse me, with the next inequality. All right, so let me finish shading this real quick here. Okay, there you go. And then y greater than x, we'll take the point, say, we'll take 0, 5 as well, but then we'll take also, say, 0, negative 5. So 0, 5 as well, and then 0, negative 5. So 0, 5. Okay, so it's 5 greater than 0. That is true. So it looks like we're shading above the line there. And 0, negative 5 is negative 5 greater than 0, and that's definitely false. So we're shading above the dotted red line. And we can see where they're meeting. Okay, so basically meeting where this region is becoming dark. Okay, so that is the solution set there. All right, that's it for this video.